Series for Associate on Software Quality. It's my pleasure to introduce Dr. Tola Geba, originally affiliated with the University of Zurich. He also did his PhD in the group of Oscar Nischkas, finished in 2005. And since then he's been a postdoc there, an independent consultant that you recognize, you see the entire, I'm just kidding, working in industry, working in the university, in both worlds basically, to transfer the good in the one and the other direction. He's actually working in an area that he calls humane software engineering, or what I also read in his short bio, critical software engineering. So I'm curious to hear more about the critical software engineering aspects in the framing of software quality. Floor is yours. Thank you. Thanks for coming.
Well, thank you. It's a pleasure to be here. So today I want to talk about software assessment, and specifically I want to say two things. I believe software assessment is a critical software engineering domain, and it must be recognized as such. And second of all, we have to approach it, even if we've done quite a lot in this area, we have to approach it in a totally different way. So that being said, let's start. So first I want to start with actually defining what assessment is. And to me, assessment is that thing we do before we make decisions. Or is that thing we should do before we make decisions. Or as I put it, assessment is a process that we want to undergo in order to understand a given situation such that we gain enough insights to make decisions. The end goal of assessment is decision making. So if we take a look, we say it's a process. So a process can be depicted into steps. And the way this process looks like, it typically looks like this. We start with an idea, with a problem, with a hypothesis. And given the data at hand, we will apply an analysis. Afterwards, we get some results. We interpret those results. If we like, if we are confident in the conclusions of those results, then we act. If not, then we repeat. So we hypothesize again, perhaps. We refine our hypothesis. We apply a different analysis. But in the end, we have to act. If this process does not end with a decision, it is not useful. This is assessment for me. Now, let's take a look at software engineering. When we think of software engineering, we think of it as building something. Hence, we typically name it development, right? It's about not having something, spending some time, and then having something. We build it. And so we call it development. However, if we really take a closer look at what developers actually do, they spend a significant amount of time not building anything. They spend it assessing the situation such that they know what to do next. And we have quite interesting studies in this area that report that up to 50% of the effort is spent on assessment of some sort. Now, let's ponder a bit on this particular figure. We are basically saying that 50% of the effort goes not on building something, but on assessing something. Now, how do they actually do it? So when it comes to practice, how do developers actually spend this 50% of time? Well, they spend it, usually they experience their software systems through the interface that they have. This is called usually the integrated development environment, the IDE, right? Now, essentially, if you strip all the bells and whistles out of it, what remains out of an IDE is a text editor. It's a super enhanced text editor, but in the end, it's really a text editor. Now, what do you really do when you have to understand a piece of software that is presented to you as a text? Well, you start reading. And so what I've done here, I just put a medium-sized system into one file, let's say about 250,000 lines of code, and now I'm scrolling through it, simulating reading. Now, just take a look at the scroll bar to the right. This is the scale of the problem. And this particular solution doesn't really scale. Let's see, suppose that you read actually quite fast. You read one line of code in about 2 seconds. It will probably take you about 1 man-month of work to read the whole thing, 250,000 lines of code. 1 man-month of work. Nobody has that time. So this solution obviously doesn't scale and is also not really accurate. But yet, developers do fall back to this solution, and this is how they typically spend those 50% of time. So basically, in other words, 50% of the overall effort is spent in the least possible productive way. Now, to me, this is a huge problem. But it's also a great opportunity. We've been in this so-called software crisis since about 50 years. And we still see all these reports saying that software systems are very hard to manage, and we still have a very low rate of successfulness. And yet, we spend 50% of the budget, for example, in management terms. 50% of the budget is spent in a totally ad hoc and totally unproductive way. So for me, this is a huge opportunity. It's not a nice-to-have thing. It's a critical issue. This is why I say software assessment must be recognized as an explicit and important domain. It's not a side issue. It's a very important domain, and it has critical importance in practice. And so, as a consequence for research must also tackle it with the consequent importance. And so, first point that I want to argue today is that assessment must be an explicit and defined as a new domain. Second of all, it's not like we have not done anything in the last 30 or so years. We've done quite a lot, but it's still not integrated. It's still not treated, the whole problem is not treated as one uniform, coherent domain. And I believe the first step is to create such a platform on top of which we can integrate what we know. And there's plenty of things that we know about how to actually approach software systems and not rely on reading code. So the second point is to integrate what we know into one coherent domain. Now the third point is that we have to go a step further than what we have done until now. And we have to go all the way to where decisions are being made, because this is what makes the difference between success and failure. If we cannot reach those that make decisions, our approaches are not useful. And so I believe assessment must also be tailored. Now what I'm talking about today is a new domain. And the new domain requires also a new way of approaching it. And I'll be talking about this at the very end. So let's start. So now to understand what exactly do we need to make explicit, we have to understand what the current state of art is. So, well, when we think of forward engineering or software engineering, we typically think of forward engineering, which is going from some high-level understanding of things to building a blueprint of the specifications and to creating an implementation that fulfills the blueprint. Now, the only problem is that the actual development kicks in, reality kicks in, and it kicks in at the level of implementation. So, several years down the road, we end up in a situation that is marked here as being messy. This doesn't necessarily mean messy in the sense of badly implemented or bad job. It simply means it does not reflect the original plan, or it does not reflect the plan that we believe in. And if our decisions are based on that, on the plan, our decisions will most probably be off when it comes to this reality here. So this is not a new thing, and then the field of reverse engineering was born in all its different shapes. And essentially reverse engineering is going from the implementation, so from a set of data, and recreating high-level views such that we can understand what the system is, so that we can take decisions. Now, let's take a look at reverse engineering. It's going from details all the way to understanding. But actually, that's not quite true, because if we look into reverse engineering, it only goes halfway. Reverse engineering is about creating the high-level views. It's not about understanding. In other words, reverse engineering is really about the technicality of producing or stripping away details to leave the essence. But it doesn't deal with the part that really counts, and that is, how do we make use of those views to make decisions? This is really important. And this is what I call assessment. And right now, this assessment part is not explicitly tackled. And I think it should be. And I also believe that assessment must be the driver force and not reverse engineering. Reverse engineering is not a goal. It's a great means. It's a necessary means, but it's never a goal. So we need to refocus our efforts such that in the end, we succeed in our goal of helping people make decisions. Now, it does not mean that that if developers rely on reading code as a primary means to understand a particular software system, it doesn't mean that they don't use any other tools. They do. So over the past several years, I had the pleasure of going and visiting companies. And I ask them typically, just as I meet them, just to get to know them, I ask them two things. Well, first I ask them, do you use any tools for reverse engineering to understand what you have in there? And they say, oh yes, they're very proud of these tools. You know, for example, they look something like this, right? Usually in the form of the dashboard, beautifully drawn. And these dashboards, they are very smart. There's a lot of the research that has been going on over the past 30 years that is summarized in these kind of dashboards. They are pretty powerful. But then I asked them one more question. When was the last time you've ever taken a decision based on the output of this tool? And they don't know what to answer. Now, this is a big problem, because it means that all these efforts of producing these interesting pictures have no impact in reality. This is a problem. Now, why is it that those things, they don't really have an impact in reality? Well, they don't really have an impact because software systems are simply too complex. There are so many details in a software system that it's extremely hard to predict what the systems will need. And so if we take a look at the two extremes, on the left hand we have text reading as a means. On the right hand we have the automatic generic way of dealing with the situation. Now, this means here that being automatic, it scales, which is great. However, being generic means that they are not really designed to answer directly software or developers' problems in their context. They are designed to answer the producer problem, the abstract problem, the one that is thought to have the value in the actual situation. Now, on the other hand, we have code reading, which is manual, which that does not scale, and still it is the preferred way. Why is it? It's because it is tailored. It's because it can deal with any contextual situation, given that, of course, it's at the lowest possible level of abstraction. So an ideal situation would be something like this. On the one hand, it should be automatic because we want it to scale. On the other hand, it must deal with the context. This is really, really important. Now, why context? As I say, software systems are really complex. Now let's see why are they so complex? Well, when we think of software systems, we think of source code, which is text. That's already large. But software exhibits itself in multiple different shapes, not only software. For example, we have the history of a software system, the way it evolved over time. That's interesting too. It also hides a lot of useful information for decision making. But that's not all. We also have tests related to source code. We also have interesting information when we run the source code, so the runtime is also important. But there's much more beyond that. We have all sorts of scripts that are around our software system, like build scripts or deployment scripts or other kinds of descriptor scripts. But that's not even all. We have, if we look into the software, into the source code, we have their programming languages. And typically, modern systems are almost never built with one single language. Usually, you have multiple languages there. And even if there is one single language, on top of that one single language, you might have multiple paradigms or multiple technologies, one stacked upon another. And even if that's not enough, on top of that programming language, you have architecture description or architectural constraints. You have the features that exercise the constraints over the system, and so on. And as I said, that's not even all. We have documentation about the system. We have specification about the system. We have mails, bug reports, chat, and other kinds of communication means. And then, again, that is not even all. That is just a small piece of it. So this is just about the data that describes interest about software system. We have all these different points of views. We have different stakeholders, and they all might want different things. Some would want external quality in terms of functionality. Some would want internal quality in terms of the structure of the system, and so on. So if you multiply all these dimensions and you consider the different possible variations along each dimension, and you consider their multiplying effect, then you will see why context becomes extremely critical, because it is practically impossible to predict what the context is going to be in the real situation. So focusing on providing a solution that will work on all systems will, by definition, will end up being generic. And this is why those kind of tools, they don't really work. And a lot of the effort that we've spent until now in reverse engineering research is really geared towards those kind of solutions. And this must be changed. And this leads me closer to my solution, the one that I propose. So I say we have to integrate different approaches because we want to deal with this multidimensionality, the multidimensional issue of software evolution. So we have to accommodate all these points of views, and we have to integrate them, we have to combine them, we have to be able to do that very easily. And second of all, we have to go the extra step and deal with the context. If we don't do that, it's almost useless. Now, let's take a look at the actual process. How do we possibly deal with this thing? And now let's take a look at the process of assessment. Here we say, well, we hypothesize, given the data, we apply the analysis. And then we interpret the results. If you're confident, we act. If not, then we redo the process. Now, the problem here is this. What happens if we don't have the analysis ready? So, what if there is no analysis that can answer or directly answer my problem, not somebody else's problem, my problem? If this does not happen, then I will fall back to reading text. So we have to provide a different alternative at this point. This is the important point. Now the alternative here is this. I believe that we have to start being able to build analysis. This should be practical. It must be really practical to build a new analysis that fits on the current context and to the current problem. And I believe this is really, really critical. And this is where the new domain lies. It's the science of crafting analysis practical and extremely cheap. For this we need all sorts of new models and we need new approaches to understand this particular problem. So now to show a bit, let's go a bit into details and see what exactly happens if you can build or craft a new analysis. And to start with, I have here a small initial experiment that we carried out. And this is on a real system. The system is called Seaside. It's a Smalltalk web application server, and we're talking here about the core of Seaside. Now, as I said, so Seaside is a Smalltalk-based application, but on top of Smalltalk, Seaside comes and builds, uses its own domain-specific constructs. So, these domain-specific constructs, they come with their own idioms. Now, if you approach the problem at the level of Smalltalk, and Smalltalk ships, for example, with a default set of rules that checks various coding idioms or various design patterns. If you approach it like this, it's called lint. It's similar to the detection in the lint program for C. Or it's similar to, let's say, find bugs or check style or similar kinds of detection programs for Java. So here we have this. We have the shape of applying that generic detection over time, and the number here specifies the number of problems per line. So in general, on average, the lint the generic detection detected about 4 problems per line in this code base. Here we have the evolution of the source code. Well, it basically didn't really evolve that much. Only here, about 25%, it increased in size. Now here, in Seaside, they built a dedicated set of rules that really specifically match the context of Seaside, so the best practices of Seaside. So here you see, well, it started with about 1 problem per line, but then it ended up with about 0. Now, how did it go there? Well, the thing was that they, after a point in this version, so going from 2.8 to 2.9, they spent explicit effort to re-engineering and clean up the system to what they consider is important. Now, both of these metrics were run, and both of them were considered during their actual re-engineering effort. And yet, only one of them was affected. Only the one that actually checked what value meant for developers was affected. The other ones basically stayed pretty much the same, even increased a bit. This is, to us, this is initial evidence that if we simply go for the generic solution, we have almost no effect. The generic detection does not reflect the interests or the value of developers. Now, this is not specific to Smalltalk. For example, I recently looked at a case study, which is a Java, and here you see the interplay of various technologies on top of Java. So if Java is the base language, what you see here are the different kinds of annotations that are used in the system. And you see how they are connected with one another. So every piece of text here denotes a particular annotation, and an annotation actually introduces or is the hook for introducing a new technology into which is cross-cutting the source code. So simply looking at the Java level of at the program, we will miss the important parts, which are here. So this crafting the analysis is really, really important, and it has to be done if we want to be able to be effective. So what I will do now, I will show you a couple of case studies. As you know, I've been a consultant in the past 2 years. That was that's my primary area of activity. And so what I do, I promote this crafting of analysis. I call it humane assessment. because it's best fitted to our abilities. So on the one hand, we need something that is contextual, but on the other hand, we need something that is automatic. And so I'm arguing for this, and I'm helping companies to put this in practice. Now, what actually happens is that I typically go and I meet the company, they start describing what the problem is, and then we can see where to go. And the first step in this area is to understand what kind of systems do they have and what kind of challenges do they have. And this first particular system that I want to talk about now, it was a legacy system, 15 years in development. So they started it in Delphi, and currently they have about 1 million lines of code, I guess, or something like that. But on top of this, to promote this system to customers, they built their own layer of domain, which is based on a domain-specific language that they created, and that was used in a two-tier application. So on the top we had the user interface made out of forms, and on the lower level we had directly the database. And the way the user interface was linked to the database was through this scripting language, which was a kind of a Pascal enhanced with some SQL capabilities. So now their problem was that they've actually never really checked the system for about 15 years. So what I did there was, okay, let's see what we can do. So this is a situation that needs rectification. And they understood that they need to do something about it because things were just getting out of hand. Okay, so then we started the project. And the first thing to do was, okay, well, we create a parser, right? It's an engineering work, one might say. But actually, it wasn't quite. Because it turned out that there was no formal specification of this language. So the first thing you wanted to do was actually recover, re-engineering what the structure of the language is. And it's not quite as simple as you might think, because there was actually nobody in the room that knew everything about that language. There was always, I could always come up with a new example and say, what's this? And then say, oh, I don't know. And so in the end, well, okay, we went through this. Then we built the parser. Then afterwards, we built the abstract syntax tree, and afterwards we built the model. And on top of that, we built metrics. And on top of that, we built visualizations. And on top of that, we built tools so that people can actually navigate through their system and check their systems. It's quite a significant effort. And one of the results looks like this. This is one of this integrated development environment. It's a small prototype. So here they have all the scripts. You click on it, you have the script with color highlighting, and you see there all the references, and you see all the incoming reference, the outgoing reference, various kinds of also metrics in there. You can search through it. You can apply queries that go and traverse the abstract syntax tree, and then based on that you can define problems or locations of problems. But in the end, even if it might appear a large effort, this here took 20 days. This was the effort to do this. Now, actually, it took 20 days because this is not all you see. They also wanted the link between the scripts and the forms. And the forms were described in a totally different way. And we had to go and reverse engineering that part as well. And then we had to link this. And we had to build another model that unified and that allowed us to build queries that would traverse all this model. So in the end, the meta model had about 20 items, 20 entities in there. It was that complex. And yet, it still took 20 days. And we built an interactive tool that allowed them to actually go and look at it. Pretty much the first time that they could detect syntactic errors. In the first hour, they corrected 100 or so syntactic errors. In a critical, it's the only system that the company builds. And it's a leader in Switzerland. This is where the problem is. This is what can go out of it. This is what can happen. Now, if you think of 20 days and compare it with 15 years of development and maybe about 50 people working on it, no, 30 people working on it per year, then 20 days is nothing. It's a millisecond. It's nothing. This is what it should be to build an analysis tool. Now, the interesting thing actually of all was not only in this. They got really excited about this. And they started to see all sorts of different possibilities. And one day they got so bold that say, a technical project manager came to me and they had a small part of the system. And they came to me and say, look, tomorrow we have a meeting with management. And we want to convince them that we need time to refactor our system. Okay, and then I asked, what do you want from me? Well, what we want is we want a picture that will tell them that it's actually too complex. And then I say, okay, and it looks like this. Actually, this is an interactive tool. It's a super simple visualization. In fact, the technique that you have in here is well known as polymetric views by Michele Lanza. So it's not a fancy visualization, but it was really effective. It turned out that management was convinced the second day. Now, what does it show here? Well, the main point that it shows is that they expected, before showing the picture, people expected to see a tree of dependencies. So here we see every bubble like this is some sort of either a script or a form, so modules, let's say. And a link between them is dependencies, so one needing the other one. Now, ideally, we wanted to have something that goes from top to bottom, is beautifully organized. In reality, it was not beautifully organized, right? This is basically what you see. Now, they could also go through and interact with this whole piece and navigate through it. This was done in one day. Okay, so this was one case study. I'll come back to those a bit later. Now, let's talk about another case study now. Well, when you have a domain-specific language and this is the language that is used by everyone in the system, you might think, well, okay, it's obvious that I need something for that language. But sometimes the problem is not so obvious. Sometimes it's much more subtle. For example, I saw another company, and this company, they had a pretty large system, again, about 12 years, critical system, and pretty large, about 500 man-years of effort invested into it. And then so we were talking, and then we said, yeah, we have problems building up a new module. Every time we build up a new module, we have real big problems, one of the developers said. And then he said, well, I'm the only one that succeeded to do that in the past couple of years. I said, oh, that's interesting. And then he said, well, I'm an external. Okay, so that was a bit of a problem. And then, so we worked a bit together and said, okay, but what kind of a system is it? And they said, well, it's Java. Fine. Now, what kind of Java? How do this, why do you have troubles putting it? Is it because they call each other or so? Oh, actually, the whole system is put together through configuration files. So what do you mean? Well, we have all these XML files that configure the relationship because we deploy the whole thing into a big workflow system. So we just have to configure them. And we have to configure them with some XML files and some action scripts. I was like, oh, that's interesting. How many of those do you actually have? Oh, I don't know, maybe some 50 or 100. And then we took a look. They had like 1,500 of those. And said, well, maybe we should build a tool that, captured the complexity of the problem. And then indeed, well, we did that. Now again, we have the same problem. And the problem was nobody knew what the description of the XML was, right? I mean, they just said, well, it's XML. Yes, it's XML, but we don't know what is inside. And the problem here was that not even that they didn't know what the schema was, but inside the same XML, you could have about 3 or 4 different possible schemas. So 3 or 4 different ways of expressing the same thing. And then all these had to combine with an action script. So another kind of scripting language that was outside, it was somehow affecting what was defined in here. Really, really complicated. So we had to go through all the pain and understand this particular system, and these were the modules, these were the Java, inside each of these is Java. But then we built the parser, we built this abstract syntax tree, we built the model, and on top of that we built the visualization just to understand what the different dependencies are. Now, this is not a toy. This is a critical system for this company. If they can't produce another bubble like this, they stay behind their competition. And they are leaders in Switzerland. This is really, really important. And then we went the extra step and we built a nice tool for them so that they actually start to at least be in position to understand the complexity of their problems. This is what crafting analysis should be. Because this, actually, the effort behind this is about 10 man-days. Again, this is nothing if you compare it with the overall effort. Now, this skill must be extremely available to everybody because it's so important. Without this, you don't know what you're doing. Now, why did I show them? You might say, well, this is nice engineering work. And I'm here to tell you that it's not. It was possible to make these things in about 10 to 20 days because of the research that is behind it, because of the models that make this thing possible. For example, behind this picture, after the effort of getting out the data, producing the picture was a matter of minutes. And so for this, what we needed a nice enough abstraction that we can use on what data we have to produce the kind of tool that we need. And then this here is called Mondrian. It's a kind of a domain-specific language that is just transform data into a picture. So it's a transformation engine for visualizations. Now, this is a piece of research. It was published in 2006. And it goes beyond just simple assessment. It goes beyond reverse engineering. It goes almost into the realm of forward engineering, because it has a border of programming language research too. It's at the border of modeling research too, because it's a transformation language. This is what makes this effort not engineering. We need more of these models. We need to make this process as easy and as painful and as affordable as possible because it's so simply critical. Now, let's move to the next one. We have this IDE here. Now, behind this IDE, there is another piece of work. It's another model that applies a component model to model browsing. So what makes browsing, and we have an engine that captures that. It's called Glamour. And this makes the whole building of this browser extremely painless. So again, building the browser is a tiny effort in this case as compared to the rest of the effort. This is because the model is there or is being built. Now, where is the challenge then? Well, the challenge goes pretty much like this. If we take a look at this browser here, in essence, it pretty much looks like this beautiful browser here. This is Eclipse, by the way. This is standard Java development. Is an industry-wide accepted tool to develop extremely serious and valuable systems. But conceptually, they look pretty much the same. You know, you have some way of navigating, you click on it, you get the text. Pretty much you get here, plus some more benefits. But to me, this is extremely rudimentary. Because in the end, this is a text editor. This thing needs to be rethought completely. There's so much space to create new models, new approaches to tackle this problem at a different way. Not that creating the tools that will be directly used in practice, but to provide the platform and enable people to build whatever they need to deal with their situation. This is where the challenge is. So, I'm arguing we have to integrate what we know, and we know a lot. We know a lot about modeling, we know a lot about data mining, data collection, we know about how to visualize, we know about how to measure, how to query. We all already deal with a lot of the technicalities of which were really hard to master. But now it's time to go the extra step and integrate them into this to serve the actual goal. And the goal is decision making. So it must be integrated, and most important, it must be tailorable. Somebody has to be allowed to take that particular approach and just use it in practice. For example, in the visualization that I showed you, it's a simple visualization. I mentioned it's based on polymetric views. Now, when people think of polymetric views, they most probably will remember a specific polymetric view, like a system complexity or a class blueprint. Now, that's great. That's a great piece of work. But the very essence is the polymetric view. That is the ability to map metrics on a graph. This is what matters. This is where the value is. And we have to strive to go towards that kind of value, the kind of value that is then replicable in many different instances afterwards. So that somebody just spends 5 minutes and applies it and solves their problems. This is where the challenge is. Now, this to me is a pretty big problem. And I believe that we have to totally change the way we do research too. Because if we will continue to do research the way we do it, we will most probably not go in another place than we used to. And what do I need? What do I mean by that? Well, first of all, I believe we have to collaborate. This is way larger than an individual, and it's way larger also than a group, a research group. It's much bigger, the problem. And so we have to collaborate. But the other problem is that in this particular area, this is an engineering discipline. And in this area, we need to be able to handle real situations. We need to be able to handle real data. We need to be able to scale our approaches. And for this to happen, we need tools. There is almost no way around it other than manual labor, which we don't want either. So then what follows afterwards is that we need tools. And in fact, if we look into what people do actually spend engineering time during their research. But it's not explicit. And I believe this does not service us. We have to explicitly approach the engineering problem in research. Because without it, we won't be able to integrate properly. Everything will be halfway there. In theory, it will work, but not in practice. And in the end, the status quo of people not making decisions better will not change. So now, I want to talk about the experience that I particularly have in being at the center of the MOOS project. So the MOOS project is a platform for software and data analysis. It started at the University of Bern in 1996. So 15 years ago, it's already a legacy system. It accumulated more than 150 man-years of effort, and we recently went past the 200 plus number of publications. Scientific peer-reviewed publications around this platform. So it's a platform that was built almost entirely in research. I say almost entirely because some of us periodically go and become consultants. But other than that, the effort was totally in the research context. And the idea here was, the basic idea is how to create an environment that has as a result us reusing each other's engineering efforts. Because I need somebody else, I need the engineering effort, but I don't want to spend it all by myself. And if we think that, for example, somebody that needs to just work on an algorithm for a particular analysis does not really care about how the data got into the system, right? then he should also not spend the engineering effort to deal with this issue. However, the issue of collecting data, of mining data, of cleansing data, is the realm of somebody else. Of modeling data is yet the interest of somebody else. And so this person here, if he will collaborate with this one and with that one, they will share the efforts. And the solution just simply emerges. It's not science fiction. It's not a super effort. And it just simply works. It's a different model. Now, let's take a look at one example. So this is a particular analysis. It's a ready-made analysis. And it's typically what you have when you read a paper. It's a beautifully packaged analysis. Nice to fit into 10 pages. So here it goes all the way from a case study to producing a picture. What exactly you see here? Well, you see classes, so it's a matrix of classes of JEdit. This is a Java system. And what you see in there is a correlation of the way they use words in the source code. So each class was considered as a piece of source code, a piece of source text, and inside, when a pixel is dark, it means it has a 100% correlation between the two classes, and when it's not, then it doesn't. Now, what you have here is also clusters of classes that are related, so it's just an analysis that go all the way from parsing to producing the picture. Now, if you actually decompose it, you will see that there are multiple steps in there. So you have data collection, data mining, you have clustering, you have visualization, and you get this one. Now, if this is a blob, if this is a big block, then you can't reuse anything out of it. You can only reuse from here on. But if this is not a blob, if this is designed in a different way, then you can apply a different step and obtain a different outcome, a different analysis. This is where the multiplying effect comes in. And this is where the benefit of investing in the infrastructure comes in. Now, how do we get there? Well, we get there through collaboration. This is a study of the system until 2007 of the different ways in which people committed code together. Now, this is not really important as what names are in there. What's important is that the system is built out of the interaction. Just because two people talk to each other, they create a client-provider relationship. And because of this client-provider relationship, the system becomes more modular, because it's not exercised only in one context, it's exercised in multiple contexts. It's plain and simple engineering. So the point here is, we don't have to spend more engineering time. We have to spend smart engineering time. And our model is an open source, is a normal open source process that basically utilizes a part of the research effort and builds the infrastructure. And because we have this infrastructure, this is a recent graph of all the publications, of all the authors and how they collaborated in the system. Because of the infrastructure, we can produce new ideas, and we can put them in practice, and we can test them, and we can build empirical studies on top of it. And all this is possible because it's practical. And I believe this is the way to go. So, if we want to step back, the first thing I want to say is that software assessment is a critical domain that must be recognized as such. And that we have to take what exists until now and integrate them all into this new domain with the goal of solving the one problem that counts, which is improving decision making. And to make this happen, we can't ignore the context, because simply we can't predict the context. And to make this happening, we have to rethink the way we do research. And instead of really just focusing on direct, nicely publishable results, I believe we also have to invest in the infrastructure, because then we can scale. Now, I call this holistic because it must go from all these points must be tackled somehow simultaneously. And you might think holistic is challenging and maybe too ambitious, but I believe that doing it any other way is simply not effective. Thank you.
Thank you.